All right, so welcome to the last day of the IMA workshop. And so our first talk of the day will be by Ankur Moitra from MIT, and it will be about learning of restricted Boltzmann machines. The floor is yours.
Great. So thanks everyone for joining us virtually. It's too bad we can't do this in person, but I guess this is the new normal. So I'll be talking about learning restricted Boltzmann machines, and this is based on joint work with Guy Bressler and Freddie Kohler. Actually, Freddie is graduating this year, so I thought I'd mention that as a little bit of a plug. But let me tell you first some of the background, because this talk really fits into the broader theme that's going to be talked about in the later talks today too, about learning graphical models. So you're going to see all about graphical models today, but graphical models are really just a rich model for defining high dimensional distributions in terms of their dependence structure. So let me start off with one of my favorite types of graphical models, which is called an Ising model. So an Ising model is just a way to specify a distribution on plus minus 1 to the n. Now, the way that you do it inherits some very interesting graph theoretic structure that governs its conditional independence properties, which I'll talk about in a minute. But first, let me define algebraically what the model is before we get into its properties. So if you look at some particular configuration, little x, that's just the choice of some vector in plus minus 1 to the n, then the probability of your random variable being equal to that configuration in the Ising model is proportional to the exponential of some quadratic term and some linear term in x. So here, this first term is the quadratic form of the vector x on the interaction matrix. So you should think about the interaction matrix as governing whether or not a pair of variables are likely to have, are more or less likely to have the same spin, either be both plus 1 together or both minus 1 together, or be opposites. So depending on how you set the interaction matrix, you're either penalizing or giving some kind of benefit to matching spins. And you also have this other vector h, where you take the inner product between h and x, and that also affects your underlying probability distribution. The way that you interpret it is that each one of these h sub i's is an external field. So if you set it to something that's large and positive, then you're actually going to incentivize the spin to being plus 1 and the opposite for minus 1. Now here, you usually think about it as the probability distribution is proportional to this exponential term, and whatever happens up here is usually called the energy. And you also have some sort of normalizing constant z, so that the entire thing is a distribution. And z here is called the partition function. So there are all kinds of generalizations, all kinds of other graphical models that you might want to study, but this is already very interesting, the Ising model. But let me just mention some of the extensions that, that you might see in other papers or in other talks today. So there are generalizations where you can consider things like larger alphabets. Maybe I don't just want each variable to be binary, either plus 1 or minus 1. Maybe I want to consider, any one of a discrete set of possibilities, and that's called a Potts model. And you can also have higher order interactions, because maybe it's not just pairs of spins interacting with each other. Maybe it's triples of spins or quadruples, and we'll see, some elements of that later. And there are also ways that you can make the underlying interactions be directed and asymmetric. So here it's symmetric, because what we do is we assume that this matrix J is symmetric, and we're just taking quadratic form. So the interaction between I and J, the amount that I's spin influences J, is actually the same as the amount that J's spin influences I. So in any case, we have our basic definition of an Ising model, and we could talk about lots of wonderful learning problems associated with it. But first, let me give you a flavor for what's nice about this model and how you can look at the interaction matrix and try and get some kind of intuition for what the distribution's key properties are. So what's really helpful in a lot of cases is to marry this probabilistic structure with a graph theoretic structure. So we have n variables because we had n-dimensional plus minus 1 vectors. And we can think about a graph on n nodes, where each one of the nodes represents one of those underlying n variables. Now we can define an edge set, which will be on pairs of these variables, xi and xj. But we only put the edge in the graph if the interaction is non-zero. So if we look in the corresponding interaction matrix, J, and we look in the ith row and jth column, if the entry is non-zero. And remember that we're thinking about J's being symmetric here, so we really do produce an undirected graph when we do this mapping from the underlying algebraic definition to the graph theoretic one. And the key property, why it's useful to look at the graph structure is because it encodes the conditional independence structures in the model. So two nodes, if we look at xi and xj, they're independent when we condition on some other set of nodes if that set of nodes is a separator. So if, for example, we take u being a set, so it's some set of the xi variables, and we condition on all of those spins, then if we have the property that u blocks all paths in the graph between I and j, then the key point is that xi and xj are guaranteed to be conditionally independent when you condition on this set of nodes x sub u. So this is the key property, is that the graph structure encodes something about how complicated the dependencies are in our underlying model. And now, as I alluded to before, we're going to be thinking about this from the perspective of theoretical machine learning. So I want to ask all kinds of learning questions associated with these graphical models, specifically about Ising models, though you could ask about it, for any of the other models that I briefly alluded to in the previous slide. So the basic question that I'm going to be interested in is the learning problem. So what if you're given samples, which are plus minus 1 to the n vectors, and you're promised that they really do come from an Ising model? Under what conditions can you actually provably learn the underlying graph theoretic structure and maybe even the interaction matrix and the external fields from not too many random samples and with a computationally efficient algorithm? So these are the kinds of questions that I'm going to be interested in, but actually I'll be interested in these questions with a twist. So first, let me just study this basic question and tell you, what's known. So this problem has a long history of study, actually goes way back to 1968, where Chow and Liu gave a really powerful algorithm, which works whenever the underlying graph structure is a tree. So, trees are very easy because, then when you take any pair of nodes xi and xj, there's a unique path between them. So there's just a single node that acts as a separator between I and j so that they become conditionally independent. And you can actually leverage that conditional independence structure, and that's what the Chow-Liu algorithm does. Is what it does is it actually defines a notion of mutual information between pairs of nodes, and it just greedily chooses the edges that have the largest mutual information, and that actually provably recovers the underlying tree structure. Now, in learning graphical models, much like in the rest of, maybe more classic combinatorial optimization, you can do all kinds of things on trees that you just can't do in general graphs. So, it really is non-trivial to figure out how to extend these to other classes of graphs to understand what you can and can't do. So there's a slightly older paper of Cargo and Cerebro, which studied this in a packed learning style model, and they gave a polynomial time algorithm on graphs of bounded tree width. So I'm not going to go into what bounded tree width is, but it is a natural generalization of trees that's very natural in its own right and lends itself to some extensions to the usual dynamic programming algorithms. But I think the closest work in spirit to the types of things that I'm going to talk about is this really elegant work of Guy Bressler, which did something pretty surprising. So it gave a polynomial time algorithm that works on graphs of bounded degree. So if you give me some upper bound on the degree that every node has degree at most 10, then it'll run in polynomial time and take a polynomial number of samples, actually logarithmic number of samples. Now the catch is that the dependence on the degree is pretty bad because it's actually doubly exponential. It's 2 to the 2 to the d. Now what was so remarkable about this result, at least for me, is that what was really neat is that he didn't need anything really beyond bounded degree and some weak identifiability conditions, which is pretty surprising because there are other problems you care about in learning, like what happens if I give you the graphical model? Can you perform sampling? And can you perform inference? So the really big surprise for me, although it's not going to play a huge role in this talk, is that that result works even in settings where you can't actually do sampling. So you can't sample from graphical models that have really long-range dependencies, but you still can learn them if someone actually managed to give you samples from that model. So in any case, there were improvements that were really interesting. So there is an improvement by Vouffray et al. I think Vouffray is the next speaker, which improved the dependence on the degree to being singly exponential, and an improvement due to Clivens and Mecca that makes some really nice connections to regression. And singly exponential is actually optimal, it turns out. So these algorithms are, the best you could hope for in terms of sample complexity and roughly in terms of algorithmic complexity. And I should mention that there's this notion which is having no long-range correlations, which, I'm not going to define it precisely, but what it means is that if you look at any node in this graphical model, that there aren't nodes that are very far away from it that have large influence. So somehow your influence dies out, and that allows you to break up your graphical model into some constant size pieces and learn them separately. So there's a work of Bressler et al. And of Ravi Kumar et al. That give algorithms that work under a variety of conditions. But what they need in particular is they need that there are no long-range correlations. So this was all just background about what's known right now, these days, about learning graphical models. And I'm going to study this with a twist that's very important for modern machine learning models, because there's something that you do that makes your graphical model much more complex, but much more expressive and widely useful, which is the notion of introducing latent variables. So, what happens if you don't actually observe the full configuration of spins? So there is an underlying Ising model that's generating your data, and it's an underlying Ising model on n variables, so it generates a plus minus 1 to the n vector. But the catch is that you don't get to fully observe that vector. What if you only get to observe some of the coordinates in that vector? So the remaining unobserved things are called latent variables or unobserved variables. And the issue is that even though you started off with this nice, elegant graphical model, which had a nice conditional independence structure, the fact that you're removing nodes and marginalizing them out actually changes a lot of the conditional independence properties. But it's still important because what this allows you to do, which is great in terms of the expressive power, but really challenging algorithmically, is that it allows variables to influence each other through unobserved mechanisms. So the real reason you care about this is that, a lot of times you have a bunch of data, maybe in a scientific application, and your goal is to find these kind of unobserved latent variables because that's the science you're trying to discover. And usually what you do is you try and guess some sort of latent variables that give you parsimonious explanations of the relationships that you can observe. This also plays an important role in things like deep learning because, actually when you add unobserved latent variables, that allows you to build much more complex models, which you then, in some of the first instantiations of deep learning, like deep belief nets, you layer on top of each other so that you can produce really wild hierarchical structure in your distributions. That's very challenging to learn from. So, with that philosophy aside, let me tell you concretely what's the problem that I'll be interested in. And it's called a restricted Boltzmann machine. It was popularized by Hinton back in the 80s. And it has really wide range of applications, but it's a very simple extension of the thing that I already told you about Ising models. So imagine that you have two classes of variables. You have observed variables, x1 through xn, and they'll take on plus minus 1 values again. And you have latent variables, y1 through ym. And again, they take on plus minus 1 values. Now, what you do is you define a distribution that's a joint distribution on the x's and y's, and it looks just like the thing that you've seen. There's an interaction matrix J, but now it's it's X transpose times J times Y is the contribution of the energy. And then you have two different external field terms, one for X and one for Y. So the way to think about this is that actually all this is an Ising model because it's the same thing we had before. The difference is that the underlying graph structure, if I define a graph on the n variables which are observed and the n variables that are latent, and I add edges for when there's a non-zero interaction, then the graph structure that I get out is now a bipartite graph because you only have interactions of observed variables interacting with latent variables and vice versa, other than the external fields. So now the catch is that you don't observe the latent variable, so it's not actually an Ising model. So all you're doing with a restricted Boltzmann machine is you take a bipartite Ising model and you marginalize out one of the two sides. And Hinton and his collaborators over decades actually showed that restricted Boltzmann machines had lots of beautiful applications, even long before deep learning. They were doing some pretty amazing things in feature extraction, collaborative filtering. And later, one of the things that made them famous was that they were the first building block for powerful modern deep learning. Back in the day, when deep learning was mostly done through unsupervised learning methods, like back in 2005, what you would do is you would take these restricted Boltzmann machines and layer them on top of each other, and you would create very complicated distributions on the observed variables that you would then try and learn in a layer-wise fashion through things like contrastive divergences. All right, so this is just more of history, but we have a model that we care about. And let me ask a basic algorithmic question. Are there efficient algorithms to learn restricted Boltzmann machines? And shockingly, this question is basically completely wide open. And it's not even going to be that much more closed after our work. I'll tell you some powerful algorithmic results. But one of the reasons I wanted to give this talk is because there are tons of open questions here that I'm happy to tell you about briefly at the end of the talk, and maybe as good fodder for the discussion at the end. But let's focus on this for now. So are there efficient algorithms for learning restricted Boltzmann machines? So in fact, there's a conceptual challenge that happens, right? Which is, what happens when you take a node and you make it unobserved and you make it latent? Well, before, what it was observed, it had a very simple dependence structure. Once you condition on it, well, if it's in a tree, then its neighbors become conditionally independent. But the issue is that, in general, when you remove that node and marginalize it out, you create a higher order dependence on its neighbors. So let's see a simple pictorial example. Even if I'm back in a very simple setting like a tree, I have the star graph, and I know that this node in the middle has the property that when I condition on it, the leaves become conditionally dependent. And that's a beautiful property to have algorithmically. It's very useful and it's very easy to exploit. But the trouble is that when I marginalize out that central node, then I actually create a higher order dependence on the observed nodes. My resulting distribution is no longer an Ising model. It's actually something more complicated that has a degree 3 interaction. So in particular, the joint distribution on the leaf nodes, when you marginalize out this root node, is no longer an Ising model. So I guess maybe the first question we should ask is, all right, so what type of distribution is it? So in fact, it's something that I alluded to before, which is it's a type of Markov random field. It's actually a binary Markov random field. So Markov random fields, they work basically the same way as Ising models. You have some energy function that goes in the exponent, and you have a partition function z, that's your normalizing constant. But the catch is that now, instead of this function f being a degree 2 function that has this quadratic term for the pairwise interactions and a linear term for the external fields, it's a degree r polynomial. So it's some degree r polynomial in these binary +1, -1 variables in the x's. So that is a binary Markov random field. And this is a folklore fact. I'll just assert it. I'm not even sure what the original source is for this fact, but basically everyone knows it in the area. So the marginal distribution on X in a restricted Boltzmann machine, where the latent variables have degree at most R, well, you could create an order at most R interaction on the remaining neighbors when you marginalize out. And that creates something that for sure fits into the class of order R binary Markov random fields. So, there's something trivial we could do for trying to learn restricted Boltzmann machines of bounded degree. We could just try and learn their joint distribution on the observed nodes as a Markov random field. But now there's a big problem with it. Are there efficient algorithms for learning Markov random fields of order R? Well, kind of, but kind of not. So in fact, it turns out that there are n to the r time algorithms for learning order R Markov random fields. So now it's not some f of r in front of the n, but the r really shows up in the exponent. So as soon as you're degree 3, 4, 5, all of a sudden, these things are polynomial time only in name. They're quite unwieldy, even though they really do run in poly time for constant r. So that's the trouble, is that these are the best state-of-the-art algorithms for learning order R Markov random fields. And actually, what's worse is they're kind of the best you could hope for, because under standard hardness assumptions, you can't hope to learn an order of Markov random field in better than n to the omega r time. So this is the relevant background. As we started off with Ising models, we talked about the history of what's known about learning them. We talked about what happens when we have latent variables and how it becomes a more expressive class. But maybe Markov random fields isn't the right way to think about these restricted Boltzmann machines because it's just too hard a problem. In fact, for those of you who are curious, the hardness assumption is the notion of sparse parity with noise. And the idea is that you can embed a sparse parity with noise is actually a very simple order R Markov random field. In fact, one which just has a single hyperedge. So that's kind of nasty. And even worse, it produces bounded degree Markov random fields. So, let me ask a revised question instead, which is, can we learn restricted Boltzmann machines better? So can we learn it much faster than n to the d time when they're bounded degree? Maybe we can learn them in f of d times poly n n times so that we can actually get algorithms that honestly can be run and are not just polynomial in name. So these algorithms, I want to mention the things that you get from learning RBMs via MRFs are kind of trivial because, n to the d is basically what you would do is you can brute force search for, some kind of separator in your graph. It wouldn't be the neighbors, but it'd be the two-hop neighbors. So these things aren't particularly interesting when you look at them from the vantage point of RBMs. All right, so now with this as setup, what can we actually say algorithmically about learning restricted Boltzmann machines? Actually, there's going to be a surprise negative result first. Let me dash your hopes before I give you some optimism. Well, I told you this folklore fact that when you marginalize out latent variables, then in a bounded degree restricted Boltzmann machine, you produce an order D Markov random field, something that at least fits into the class of order D Markov random fields. It turns out that there's actually a pretty surprising converse to that fact, is that marginalizing out nodes in a bounded degree RBM can actually produce any bounded order Markov random field. So every binary Markov random field of order T can actually be realized as the distribution on observed nodes of a restricted Boltzmann machine in which the maximum degree of any hidden node is at most T. So actually these two classes of distributions, surprisingly, are equivalent even when you parameterize them by, on the one hand, the bound on the degree of the hidden nodes, and on the other hand, the order of the binary Markov random field. They're completely expressively equivalent. This is actually a pretty surprising fact, or at least that quite surprised me, because some of the things that were known before about the representational power of RBMs were quite different, actually. Like, for example, there was the work of Martins et al., which showed that you could represent hard distributions with RBMs, but the catch was that they needed to be dense RBMs. So if you had n nodes on the left and n nodes on the right, you would have something like each node would have degree n over 10 at least. So these are things which, they're not really bounded degree, and it's hard to tell the difference between whether you're, paying an n to the d price in your running time or a 2 to the d price, because they look about the same. So, this tells us a much sharper characterization of the representational power of bounded degree RBMs, because in fact, it tells us what they look like even, on when we constrain their degree as opposed to in a dense set. So one of the corollaries for this result is that, you can embed hard problems into Markov random fields, and hence you can also embed them into bounded degree restricted Boltzmann machines, and this was not known. So what this tells you is that actually it's hard to get, it's hard to learn RBMs in time n to the little o of d. So you cannot get the naive extension of Bressler's result where you can hope for an f of d times poly n algorithm just by standard hardness assumptions, same thing as before. And in fact, it's even worse, as it's not even a hardness of proper learning where you have to spit out an RBM. It's hardness for anything that actually represents the distribution in a way that allows you to do hypothesis testing. So even if you spit out some unnormalized function, that's actually still a computationally hard problem. So that's pretty nasty. And maybe what's even worse, I guess I'm really going to dash your hopes first. Yeah, it's, if you choose D as like 10, then it's an RBM that's hard. It's an explicit thing with degree at most 10, with at most 2 to the 10 hidden nodes. So there are a constant degree and a constant number of hidden nodes. And yet the thing is computationally hard to learn. So that stinks. And I won't get into all the comparisons, but if you're a complexity theorist, feel free to talk to me afterwards. There are some interesting questions about the difficulty of proving improper learning, and we can talk about that later. So I guess maybe my real question with this negativity aside is, are there any natural and well-motivated families of restricted Boltzmann machines that actually can be efficiently learned, maybe ones with long-range dependencies? And actually the answer is yes. So it turns out that yes, if they're ferromagnetic. So in that case, what we do is ferromagneticity is defined as you assume that the interaction matrix J is entry-wise non-negative, and same for the external field. So what this means in terms of the distribution is that the spins that you observe are positively associated. When one spin is +1, it makes the other things more likely to be +1. So you can't create some pretty nasty cancellations that you could otherwise. And as a historical note, actually ferromagneticity plays a key role in a lot of classical statistical physics and theoretical computer science. It's related to things like Li-Yang theorems, where you look at the partition function as a complex polynomial, and you look at certain properties about where the zeros are, and that governs phase transitions. It's also related to when you can say that you can efficiently sample from models. So this is kind of nice because it tells us that we can learn RBMs in models where you can actually do things downstream, like doing sample and inference with them if you can learn them. So that's pretty cool. And so let me tell you the main results is that when you have a ferromagnetic restricted Boltzmann machine, you can get a polynomial time algorithm. So f of d times poly in n time algorithm, and it'll be a very simple greedy algorithm that you can honestly run that has logarithmic sample complexity for learning the underlying RBM. You need some kind of upper and lower balance in the interaction strength. Those are the usual technical assumptions, just so that you can identify where the entries in J are 0 or non-zero. And what we do is we actually output a description of the joint distribution as a Markov random field. But it turns out that these connections to phase transitions allow us to use that description to do things like to do provable estimation and inference in those models. So that's pretty neat. It's a model which you can provably learn with latent variable models, despite the higher order dependencies, despite the long range dependencies too. And you can then use it downstream for doing things like inference. So so I'll say briefly that one of the motivations for considering ferromagnetic Ising models are things like you can model the adoption of technology spread or epidemics on networks, like which people in a social network use iPhones or Androids. Usually the way that you model these things is by some iterative process called Glauber dynamics on a ferromagnetic Ising model. Because when you have more neighbors who have an iPhone, you are probably more likely to get an iPhone yourself. And it turns out that you can use these types of algorithms I'm describing to learn the underlying graph structure, even when you have latent variables and you don't observe all the nodes in these social networks and these epidemic processes. So that's pretty neat and somewhat timely. So let me, in the little bit of time I have left, I guess I'm going a bit slow right now, let me tell you about some of the technical ideas, because there's going to be a cool way that actually some old tools from mathematical physics are going to save the day. And in fact, there'll be some neat history about historical discoveries about how those relate to classic TCS tools and some surprises there. But let me tell you the key thing that I'll be interested in before I tell you how the overall algorithm works and how it fits together. There's something very important called the discrete influence function. So this will be a little bit, funny, but the way that this works is if you look at some node I, which, has a random variable x of I associated with it, that's a ±1 variable. What you can do is you can look at its conditional expectation. So what happens if you specify a set S of some nodes, so x sub s, these are a bunch of spins. And let's say that this discrete influence function, it takes as an argument a choice of, in these nodes in S, which ones you fix so it takes as an argument a set S, And then the key is that you pin all of those nodes to being +1. So you take a set and then you pin those spins to being +1. And then you look at the conditional expectation of the ith variable. This is a real valued function on sets, and it's called the discrete influence function. So it's a function from subsets, which are of n minus I to the reals, and it measures the induced bias on some node. And actually, it turns out that it has an amazing property that it's submodular. So it has this property of diminishing returns. I'm not going to precisely need what submodularity is, but you should think about it as a property of diminishing returns that, if I look at a set S and then I add another node to the set S, how much does additionally fixing that new node spin to being +1 change the conditional expectation of I? Well, that's a monotone decreasing property of the set S, because as you fix larger and larger sets, fixing any new spin to +1 has less of an effect. So it turns out, and this is the main theorem, is that for a ferromagnetic Ising model, the discrete influence function is monotone and submodular. Now, it turns out, and this is where the history comes in, which is pretty funny, is that this has been studied for a long time in related areas in mathematical physics. And it's known under the phrase concavity of magnetization. That's not going to make any sense to you until I get to the next slide. But what's really funny is that the concavity of magnetization actually has a lot to do with submodularity. And actually it predates submodularity in the discrete math, computer science community. So it's kind of funny because it seems that mathematical physicists were actually studying relaxations of submodularity before submodularity was defined. So that's kind of funny. If you have any insights about the history, come email me or talk to me after. But let me tell you about what the concavity of magnetization is, because it's a very intuitive thing. So what you can do is you can define the average magnetization. So you have these x1 up to xn that are variables. And I keep calling them spins because that's the original motivation for the Ising model, was to mathematically describe magnets, literally things which have positive association, and understand the effect of putting an external field on them and when they undergo phase transitions. And one property that you can look at, a parameter of your model, is the average magnetization. So you take a sample from your model, you take the expectation over it, and you add up these x1 through xn, and you divide by n. So you look at the average spin, whether it's +1 or -1. And you can do some neat things, which is, let's say we're in a ferromagnetic case where the interactions are all non-negative. It's ferromagnetic, and the external field, let's assume for simplicity, it's some parameter h that's everywhere the same thing. Then there are a lot of intuitive and classical results. These aren't actually the easiest things to prove, but they are intuitive, which is, what happens to the external field if I increase the external, and what happens to the average magnetization if I increase the external field everywhere? Well, that should probably only increase, right? And that's the statement that the partial derivative of m with respect to h is non-negative. That's a classic result of Griffiths. There's actually something which captures the law of diminishing returns, which is if I look at the second derivative with respect to h, then it should be non-positive. Because if I increase h by a little bit, well, how much do I increase the magnetization? That'll go down if my average if my external field was higher to begin with, because they're diminishing returns. And that actually is called the concavity of magnetization. It's proven through something called the Griffiths-Hirsch-Sherman inequality, which is something that we can use to also prove the submodularity of discrete influence. So let me actually tell you how the overall algorithm fits together, because it's pretty simple intuitively. So here's the idea is, not only is it true that if you take a ferromagnetic Ising model, well, then this discrete influence function is submodular. That's true even if you throw away some of the nodes and you marginalize them out, because that's just like restricting your set system to only looking at the observed nodes. So it's actually still, that's a trivial corollary of that theorem. It's still monotone and submodular because it's just a restriction of that same function. So now here's the key idea, is that the maximizer of that monotone submodular function, which, it's good to have an intuitive description of what this is. You have some node I that's observed. You're asking, among the other observed nodes, which one should you pin to the spin ±1, to the spin +1, to most influence the spin of that node I? Well, the maximizer of that ought to be not the neighbors of I, because those are latent variables, but the two-hop neighbors, the neighbors of their neighbors, because those are a separator in the graph. So here's the idea: is you take your restricted Boltzmann machine and you have some node I, and you want to understand pinning which set of nodes among the observed set has the most influence on the spin on I. Well, the idea is you take not the neighbors of I, because those are latent variables, but you take the neighbors of the neighbors. And if you pin those guys, that has the most influence on the spin on I. And in fact, the other guys have no influence on the spin on I because they're now conditionally independent, because these green nodes are a separator between the red node and the black nodes, at least the observed ones. So that's the intuition, is because the two-hop neighbors separate I from all the other observed nodes. And so, what's the quantitative statement? So you need some kind of non-degeneracy conditions that, when an entry in your interaction matrix is non-zero, that it has to be noticeably non-zero. Otherwise, you can't get quantitative sampling complexity bounds on how many samples you need to recover whether or not this entry is non-zero or the underlying graph structure. You also need some bounds that, some nodes, they better not have infinitely large external fields. Otherwise, they're not even going to be random variables. But with these non-degeneracy conditions, it turns out that if you have a set S that does not contain the two-hop neighbors of I, well, there is some node J that you can add to your set. It'll actually be one of the things in the two-hop neighborhood that is going to noticeably increase this discrete influence function by something that you can quantitatively bound in terms of alpha and beta. So this is a progress measure that says when you keep adding nodes that have a large influence, then when you don't have the two-hop neighborhood, there always is some way to make progress on the discrete influence function. And ultimately, the discrete influence function is something that's lower bounded by -1 and upper bounded by +1. So this process can't go on too long until you find some superset of the two-hop neighbors. This turns out to be related to things like the greedy algorithm in classic approximation algorithms for trying to maximize this monotone submodular function, subject to a cardinality constraint that I'm looking for a set S that isn't too large, because I don't want to just take all the neighbors, all the things that are in the observed nodes. But it turns out that there are bi-criteria extensions to this, where instead you go past the bound on the size of your set, so that you actually get close to the maximum of the discrete influence function. And what this allows us to do with this simple greedy process of each time you pick a node that noticeably moves the discrete influence function is eventually you learn, you run out of progress to make, and the thing that you end up with is a set that contains all the two-hop neighbors of I. So then what you can do is you can actually just prune the superset of the neighbors, and that gives you a way to learn the underlying Markov random field. So that's the basic way that the outline work, is that through a miracle, this notion of the concavity of magnetization from mathematical physics that was studied back in the 60s and 70s turns out to actually govern the notion of submodularity for the discrete influence function, which gives us a progress measure for learning the underlying graph structure in spite of the fact that we have latent variables. So I'm going to very briefly, no talk would be complete. This talk wouldn't be complete without actually telling you what the Griffiths-Hirsch-Sherman inequality is. I'm not expecting you to get any insights from it because it's kind of a mess. But, let me tell you first, the smooth influence function is that there's a way that what you can do is you can, instead of working with something that's a discrete function that takes a subset and asks for, when you pin those nodes to +1, what happens to the spin at some node I, you can instead think of varying the external field, and you can simulate the same types of things. Because in particular, imagine I want to simulate pinning the spins in the set S to +1. What I can do is I can take some external field, some vector H, and I can just set all the coordinates in that external field that correspond to S to +infinity. And what that does is if your external field is infinite, that node had be fixed, is essentially pinned to the spin +1. So the smooth influence function is just a continuous extension of the discrete influence function. And actually, in retrospect, this has been studied in mathematical physics. No one called it this before because we didn't even have that term until a decade later. We didn't even have the notion of submodularity. And it took another 2 decades for even to have the notion of a multilinear extension. But it turns out the smooth influence function is a multilinear extension of the discrete influence function that turns out to be submodular. So the Griffith-Hirsch-Sherman inequality, in case you asked, this is what it is. I don't know what to tell you. There's some x sub L variable that has to do with creating some sort of phantom x variable that acts like an external field. If you ignore that phantom thing, what's really happening is it looks a little bit like cumulants because this is to do with third moments of your distribution. But, it's weird. It has to do with like matchings and sums over them. And it's related to something called the random current method. But, really the way to think about it is that GHS inequality is the thing that allows you to prove this concavity of magnetization, the thing that I described earlier. But the flip side is that it also allows you to prove that the second order partial derivatives of the smooth influence function are all non-positive. And that's the property that a multilinear extension of a submodular function would have. So actually what we end up having to do is we have to go the other direction, is we have to go from that property of the multilinear extension to submodularity. And I'll also mention that other classic things like Griffith's inequality, they tell you also properties about the smooth influence function, like the fact that the partial derivative is non-negative. So it turns out that you can recover submodularity just from these properties of the smooth influence function just by integrating. So let me not go into all of that, but I'll show you just one proof and then I'll skip the second proof. But if I want to prove something like my discrete influence function is monotone, I want to show that this term on the left-hand side is non-negative, because when I add j to the set S, well, that's only going to increase the chance that the spin at this node I is +1, compared to if I don't add j into it. What I can do is I can express this as an integral, because I take the partial derivative of the smooth influence function with respect to hj, but I vary that from either plugging in, I add to this h prime external field something that's 0, or I vary it to +infinity. And that has the property that I'm changing from fixing all the spins in S to being +1 to fixing all the spins in S union J to +1. Now, the key property is that Griffith's inequality tells us that the thing that's being integrated is non-negative. So hence the integral is non-negative, and that tells us that this discrete influence function is monotone. Actually, it turns out same thing works here when you want to prove submodularity. That what you can do is you can set up the same integral that expresses the marginal increase when you have a set S. But the key point is you want to relate that to what happens when you have the other, what your marginal increase when you instead start off with the set T, that's a superset of S. And you want to say that the marginal increase for S is larger. And then you can instead, use an argument about the second order partial derivatives, and that gives you the proof. So it's really very simple. You just take these properties of the partial derivatives of the smooth influence function, which follow from the Griffiths-Hirsch-Sherman inequality, and you integrate them to go from the multilinear extension back to the submodular function, which gives you the way to analyze the algorithm. So let me summarize just in the last minute that I have left. So, what I told you was, first, I dashed your hopes because I told you about this exciting problem of learning restricted Boltzmann machines. It sounds like a slight twist on something that we understand really well at this point about how to learn discrete graphical models of bounded degree. But the twist is that now there are latent variables. So all of a sudden, all of our usual things go out the window because those latent variables create higher order dependencies. And yet there is a notion that despite the fact that that general class is hard and it's equivalent to another hard class, well, there are still ways that you can impose structural assumptions on the parameters that get you around those hardness results that allow you to learn restricted Boltzmann machines provably and computationally efficiently. In fact, I gave you a very simple greedy algorithm. All you do is you start with a node, and you keep adding other nodes that are observed that have a big effect on the marginal, on the overall discrete influence function. and then you prune what you have left. So there are simple algorithms. And, I think the closing question that I have really is, despite the fact that we know hardness results for general RBMs, it seems like there might be tons of classes in the space, classes of RBMs, where we can move beyond this worst case analysis and give provable algorithms and give things with good sample complexity and runtime. And maybe even these things are algorithms that we can run from a practical standpoint, depending on the application. So I'll stop there, and thanks for your attention, and I'll take any questions you guys might have.
Thank you very much, Ankur. Great talk. Are
Thanks.
there any questions? I believe that any participant can unmute himself and or herself and ask the question. So maybe to start the discussion. Oh, sorry. Please.
No worries, no worries. So, yeah, so, one of the things that we've worked on that is connected to icing models in terms of graph structures and machine learning are methods for graph cuts based on the Ginzburg-Landau energy.
Okay.
Right. And
yeah.
So I was wondering, do those kinds of like total variation type, perimeter type calculations come into this work, or is that something really quite different?
It seems potentially pretty different, but let me give you one connection. Sure. Back when I was talking about the history of learning graphical models, and let me answer your question more for learning graphical models without latent variables.
Right.
There was this older paper of Karger and Cerebro, which worked for bounded tree width graphs. So bounded tree width is a nice, graph structure in the sense that, what you have is you have a tree structure, but each node in the tree represents a bag of vertices, and vertices appear in more than one bag. And you have some properties about how those bags cover the edges. So it's really a very natural structure that lends itself to dynamic programming algorithms, because if you knew the underlying graph structure, you could then just do dynamic programming to do sampling or inference. But the learning algorithm for Karger and Cerebro is based on graph cuts in the separate in the underlying bounded tree width graphs,
Sure.
as far as I remember. So it's not literally the same thing in the sense that I think you're referring to certainly there are things where you can use sparsest cut to do image segmentation, but there are also
Right.
PDE approaches where you can do Ginzburg-Landau that are in some sense extensions for these. And those are usually in settings where you don't have bounded tree width because you have an underlying grid graph.
Right.
But they do have some similarities in the sense that the worst case complexity of those things, as far as I know, the best analysis of those things really does depend on the smallness of the separators, even if they work much better in practice. So that's as far as I can tell. The other thing is that, there's this other works that I mentioned, this work of Bressler et al. From 2008, where they were working with the assumption that you have no long-range correlations. Right. And in that setting, you don't have small graph separators, but you have small separators in a statistical sense. Because if you look around a node and you just cut at some radius, nothing outside that radius has any large influence. So As long as you have what are called amenable graphs, that they have like bounded growth, then you have nice properties that, you always can create a small, separator that, works well enough, kind of thing.
Okay, thank you. That was very helpful.
Any other questions for Ankur? So I have one actually. So you mentioned that you had some results from the inference from the model that you learned. I was wondering if you could comment a couple of words, and just to boost the question that I have is that so you learned the induced MRF on the variables, and you showed that this is equivalent to this representation that you wrote initially, the RBM, which is Ising model with GIJs. But I was wondering if, from computational perspective, inference, these representations are equivalent. And I'm thinking about something like running a Glauber dynamics on both of these representations. And we know that, for example, even for a ferromagnetic model on like p-spin model, such as there are interactions with for example, greater than 3, there is spin glass phase, and this actually this Markov chain may not converge. Whereas for this Ising model representation, it may be easier. So my question is whether this representation
So that's a great
is...
question. In fact, it's such a good question that I feel like I might, I would have planted it normally, but, thanks. It's a subtle thing, so I didn't really want to get into it. But something weird happens is that we can learn an RBM that we can do inference for, but we cannot sample. Let me tell you why, because it's related to your question. So you learn an MRF representation of the observed nodes. And we proved earlier that that's equivalent to bounded degrees. And those are all computationally efficient reductions. So you can actually go from that Markov random field to a bounded degree restricted Boltzmann machine, and it'll be bounded degree. But there's a big catch, which is that it's not necessarily ferromagnetic. So you learned a Markov random field which can be represented as a ferromagnetic RBM, but I don't know how to find a ferromagnetic RBM that represents it given the promise that there is one. If we could, then you could do sampling because you could use Jerome Sinclair, you could use Glauber dynamics, you could use all of those things that actually show that you can learn it. So then that begs the question, why the heck can we do inference if we learned a Markov random field that is a different representation of a structure that is efficient, but we can't find that structure? It's because recently there's been a lot of beautiful progress by Barvinok and a lot of follow-on works to this about understanding phase transitions through properties of the complex valued partition function, understanding connections with phase transitions, and how you can use Taylor approximation to get algorithms. Now, there's a work of, I'm going to forget all the authors, so let me not say it, but it was, I think in Fox maybe a year or two ago, which shows that you can, do inference for these MRF types of things, provided that you have those, Barvinok-like properties, which are analytic properties about the partition function. And the MRF that we learn inherits those nice properties. So they, they gave alternative algorithms that weren't quite as good as Jerome Sinclair, but gave it through the Barvinok approach. So that's the key point, is that the MRF, despite the fact that we not turn it into, as far as I know, ferromagnetic RBM, we can still write down its partition function and do things analytically with the Taylor series where the easiness algorithmically is inherited from the fact that there exists a ferromagnetic RBM. Okay. But, let me, so let me actually mention, so the thing is that, I don't know, I'm an algorithms person. I have a hard time believing complexity results as real barriers in some cases. Sometimes I reluctantly do. But, the lower bounds that we have are kind of weird because they're degree D, but with 2 to the D hidden nodes. So it's, again, some kind of Taylor series thing where, when you marginalize a node, you create a weird dependent structure in the observed nodes. And there's a way to create a bunch of 2 to the D unobserved nodes that perfectly cancel each other out. And the fact that they cancel each other's lower order effects out, and you only get a higher order effect that you miss until you brute force and find a degree D dependence. But, one of the questions that I've wondered for a long time is, what happens if you study these things in the model of smooth analysis and you perturb your underlying parameters for your RBM? You don't create these accidental cancellations almost surely. So can you algorithmically learn it? Or what happens if you put some combinatorial structure on the RBM, like maybe it's an expander, and you can't have 2 to the D things, somehow magically canceling each other because they all have all their edges into a size D set. So all of these things I think are fair game. It's just that we have to be, cognizant and, avoid the fact that we can't learn these things in general. There are genuine hard cases, but now I think the game is to identify interesting classes that you can learn.
Great, thank you very much. That's helpful. I suggest that we move to the breakout room where we can continue discussion for the next 15 minutes before we have the next talk. So could you please push us to the breakout room?